everyone, we're Mimicker, here to introduce all kinds of knowledge, even the stuff we didn't know about. Last time, we talked about Professor Richard Maslin's book, Seeing with the Brain. From eye to mind, from perception to thought, exploring the mystery of seeing.
Yeah, that was a fascinating look at how vision isn't just, taking a picture.
Exactly. The book really challenged that old idea of seeing is believing. It showed us that vision is, well, actively constructed by the brain.
It really did. And that leads us perfectly into what we're exploring today, illusions.
Right. Because if the brain is building our reality, sometimes that building process goes a little bit differently than physical reality.
Precisely. Systematically differently. So our mission today is to dive into these deviations, these illusions, and try to understand first why they happen.
And second, what they actually tell us about how the brain works. It's kind of like looking at the exceptions to understand the rule, isn't it?
That's a great way to put it. And the big shift in perspective, really, is moving away from seeing illusions as just mistakes, errors, defects in the system.
Yeah, that used to be the common thinking, right? Like, oh, my eyes are playing tricks on me.
Exactly. But the modern view, from psychology, from neuroscience, is that illusions are often unavoidable byproducts. They're what happens when a highly efficient system has to make a quick decision, its best guess, often with incomplete or ambiguous information.
So they're not bugs, they're features. Or maybe like side effects of features.
Side effects is a good term. They give us this incredible window into the brain's operating principles. Scientists can almost use them to reverse engineer how perception is built.
Okay, before we get into the different types, let's make sure we're clear on the terms. For you listening, what's the hard line between an illusion and a hallucination? Because they sound similar.
They do, but the distinction is crucial. It all comes down to the external stimulus. An illusion is a misinterpretation of something that is actually there, an external stimulus that's present.
Okay, it's like mistaking a coat rack in a dark room for a person. The coat rack is there, you just interpret it wrong.
Perfect example. Or seeing that shimmering heat haze on a hot road and thinking it's a puddle of water. The light waves are really there, shimmering, but your brain misinterprets the cause.
Got it. So what's a hallucination then?
Hallucination is a perceptual experience, seeing, hearing, feeling something when there is no corresponding external stimulus present at all. Zero input for that specific perception.
Ah, okay. So hearing voices when no one is speaking or seeing something that isn't there, big difference.
Huge difference.
Yeah.
One is misreading the data. The other is generating data internally.
All right. So let's get into classifying illusions. Our sources seem to group them based on where the, let's call it the deviation, originates. 3 main categories.
That's right. We can start with the simplest category, physical illusions.
Okay.
These actually have nothing to do with your eyes or your brain doing anything wrong. They're caused purely by the physical laws of the environment, like optics.
Ah, like the classic example, you stick a straight chopstick in a glass of water and it looks bent where it enters the water.
Exactly that. That's just light refraction. Light travels at different speeds through air and water, so its path bends at the boundary. It's physics, not biology or psychology. Your brain is seeing the bent light path correctly, really.
Okay, so that's purely external physics. What's the next level up?
Next up are physiological illusions. Now we're involving our biology. These illusions stem from the way our sensory organs, like the retina, or the neural pathways immediately connected to them, function or get temporarily fatigued.
Ah, like after images. If you stare at a bright green shape for a while and then look at a white wall.
You see a magenta after image, right? The complementary color. That's because the photoreceptor cells that detect green have become fatigued, less responsive for a moment. So when you look away, the other color receptors are temporarily stronger in comparison.
So it's like a temporary glitch in the hardware because you overworked it.
Pretty much. Another set of examples here involves something called lateral inhibition. This explains things like Mach bands or the famous Hermann grid illusion.
The Hermann grid? That's the one with the black squares and white lines where you see ghostly gray dots at the intersections, right? But they disappear when you look directly at them.
That's the one. And lateral inhibition is the reason. It sounds complex, but it's actually a fundamental process in our visual system.
Okay, so what does it do? Why do we have it?
It's crucial for enhancing contrast and detecting edges. Basically, when a neuron in your retina is strongly activated by light, it tends to inhibit the activity of its neighboring neurons.
Why would it do that?
Think about seeing a sharp edge between black and white. The neurons seeing the white side are highly active and strongly inhibit their neighbors over on the black side. The neurons seeing the black are less active and weakly inhibit their neighbors on the white side. This push-pull sharpens the perceived contrast right at the border, makes edges really pop.
Ah, okay. So it helps us see boundaries clearly, which is obviously useful. But how does that create the ghost dots in the Hermann grid?
Well, at the intersections of the white grid lines, a neuron is receiving more inhibition from its neighbors all around it, in the white horizontal and vertical lines, compared to a neuron in the middle of a white line, which only gets strong inhibition from two sides.
So the neurons at the intersections are sort of dialed down a bit more.
Exactly. They fire less strongly, and your brain interprets that reduced firing as, well, a little bit of grayness, a shadow. But when you look directly at an intersection, different retinal processing takes over, and the effect vanishes. It's a byproduct of that edge enhancement system working maybe a bit too hard on a regular pattern.
Wow. So a helpful mechanism creates this weird side effect. You also mentioned the expanding hole illusion. That sounds intriguing.
Oh, it's a relatively new one, but very powerful. It's typically a black, fuzzy blob on a patterned background. When you stare at it, a large majority of people, something like 86%, perceive the central black area as actively expanding, like you're falling into a dark tunnel.
And that's physiological, not just you thinking it's expanding.
Well, the perception is subjective, but it triggers a measurable physiological reflex. Your pupils actually dilate. Your brain interprets the illusory expansion as moving into darkness and automatically tries to let more light in.
Whoa. So your body reacts physically to something that isn't really happening. That's pretty wild.
It really shows the deep connection between these visual inputs and our basic physical responses.
Okay, so we've had physical, then physiological. That brings us to the third and probably the most complex category, cognitive illusions.
Right. Now we're moving beyond the sensory hardware and into the software, so to speak. This is where top-down processing comes in. Our perception isn't just built from the bottom up, from the light hitting our eyes. It's heavily influenced by our existing knowledge, our assumptions, our expectations, our memories, everything we already know about the world.
So the brain is actively interpreting, not just receiving.
Actively, constantly interpreting. This idea actually goes way back to the 19th century, to the scientist Hermann von Helmholtz. He proposed that the brain makes unconscious inferences, essentially, educated guesses, to make sense of sensory data. Cognitive illusions often happen when these inferences, these top-down assumptions, lead us astray.
Okay, so if cognitive illusions are about interpretation errors, how do we break them down further? Our sources mention a typology based on how they trick us.
Yeah, we can categorize them by the kind of perceptual error they produce. First, you have ambiguous illusions. These are images or objects that can be perceived in two or more distinct ways, and our brain tends to flip between the interpretations.
Like the Necker cube. You can see it as if you're looking down on it or looking up at it, and it just switches back and forth.
Exactly. Or Rubens vase, where you see either a central vase shape or two faces looking at each other in profile, and your perception flips between those two stable states. The input is constant, but the perception is unstable.
Okay, ambiguous. What's next?
Then you have paradox illusions, sometimes called impossible objects. These are my favorites. They are 2D drawings that depict objects that could simply not exist in 3D space, defying the laws of geometry.
Ah, like the Penrose triangle or those mind-bending staircases in M.C. Escher's work?
Precisely. Escher was the master of this. Think of his waterfall, where water seems to flow uphill, or ascending and descending, with monks forever climbing or descending stairs. They look plausible at first glance, but they violate basic geometric logic.
They really mess with your head. Okay, third type.
Third are fictional illusions, also sometimes called illusory contours. This is where the brain perceives edges, shapes, or surfaces that aren't physically present in the stimulus. It literally fills in the blanks.
The classic example here is the Canessa triangle, isn't it? Where you see a bright white triangle sitting on top of 3 black circles with wedges cut out, even though no triangle is actually drawn.
That's the one. Your brain creates those white edges connecting the Pac-Man shapes because it infers that a triangle must be there, occluding parts of the circles. It's constructing a meaningful shape from incomplete data.
Filling in the gaps to make sense of it. And the last category.
The last major group is distorting illusions. These are perhaps the most studied. They're characterized by distortions of size, length, curvature, or angle.
Ah, okay. So this is where things like the Müller-Lyer illusion, the lines with the fins that look different lengths, or the Ponzo illusion, the lines on the railway tracks fit in.
Exactly. Or the Ebbinghaus illusion, with the central circles appearing different sizes depending on the surrounding circles. These all involve a misjudgment of geometric properties.
So we have these categories: ambiguous, paradox, fictional, distorting. Now, what are the deeper psychological mechanisms causing these cognitive illusions, especially the distorting ones? You mentioned top-down processing, but how does that work?
Well, one major framework comes from Gestalt psychology. Its core idea is that our perception isn't just about sensing individual bits, docks of light, tones, but about organizing those bits into meaningful wholes, or gestalts. The famous phrase is, the whole is different from the sum of its parts.
Right, Gestalt principles like proximity, similarity, how do they explain illusions?
Well, the figure ground principle helps explain ambiguous illusions like Rubens' vase, what becomes the figure faces, and what becomes the ground vase. The closure principle, the tendency to see complete figures even when parts are missing, is exactly what's happening in the Canissa triangle. And multi-stability describes that flipping perception in things like the Necker cube.
Okay, so Gestalt helps with organizing perception, but what about the size distortions like in Ponzo or Müller-Lyer? Is that Gestalt too?
Not directly. For those, a key explanation lies in perceptual constancy, specifically size constancy. This is a really fundamental adaptive ability of our brain.
Constancy, meaning keeping things the same.
Exactly. Think about it. As someone walks towards you, the image they cast on your retina gets physically larger. But you don't perceive the person as actually growing in size, do you? No, of course not. I just perceive them as getting closer. Right. Your brain automatically accounts for the changing distance and keeps their perceived size constant. It maintains stability in your perception despite the wildly changing sensory input. It's crucial for navigating a 3D world.
Okay, that makes sense. So how does size constancy lead to illusions like Ponzo?
The Ponzo illusion cleverly uses linear perspective cues, those converging lines that look like railway tracks receding into the distance. Your brain interprets these cues as depth.
Okay, it sees depth.
So the upper horizontal line of the Ponzo illusion is positioned where the converging lines are closer together, signaling further away to your brain.
Oh.
The lower line is where the converging lines are wider apart, signaling closer. Now, even though the two horizontal lines are physically the same length on the paper, your brain applies its size constancy rule. It thinks, okay, that top line looks the same size on my retina as the bottom line, but it's further away according to the depth cues. Therefore, to look this size from that distance, it must actually be larger in reality.
Ah, so it automatically scales up the perceived size of the top line because it thinks it's farther away, even though it's just a flat drawing.
Precisely. It's misapplying a usually very helpful rule because it's been tricked by the 2D depth cues.
And the Müller-Lyer illusion, the lines with the arrow fins, is that the same idea?
That's the classic hypothesis, often called the carpentered world-hypothesis, which we'll get back to. The idea was that the fins mimic perspective cues. Fins pointing outward, like the corner of a building jutting towards you, make the line look closer and thus shorter. Fins pointing inward, like the far corner of a room, make the line look farther away, thus longer, due to size constancy scaling.
So again, the brain using depth cues from a lifetime of seeing corners and applying that scaling rule inappropriately to flat lines.
That was the dominant theory for a long time. It paints this picture of the brain constantly making these inferences, these calculations, based on experience. And this fits perfectly with the really modern neuroscientific view.
Which is?
The brain as a prediction machine. This is probably the most important idea in current perception science. We've really moved away from thinking of the brain as just passively receiving information, like a camera.
So it's more proactive.
Much more. The idea is that perception is generated through a process akin to Bayesian inference. The brain is constantly generating predictions or hypotheses about the causes of its sensory input.
Bayesian inference sounds statistical.
It is, fundamentally. The brain combines its prior beliefs, basically, everything it's learned about how the world usually works, its expectations with the incoming sensory evidence. It weighs these two things to arrive at a posterior belief, which is what we actually perceive. Our conscious experience is the brain's best guess resulting from this process.
Whoa. So perception isn't just reading the world, it's the brain's interpretation based on its predictions.
Exactly. Neuroscientist Anil Seth puts it very provocatively. He says perception is a kind of controlled hallucination. The brain is actively generating our reality based on its model of the world, constantly updated by sensory input.
A controlled hallucination. That's a mind-bending idea. Does that mean we're never really seeing objective reality directly?
In a way, yes. We're always experiencing the brain's interpretation, its best fit model. A fantastic demonstration of how our prior beliefs can literally override the raw sensory data is the checkerboard shadow illusion.
Ah, yes, the one with the cylinder casting a shadow on a checkerboard. Squares A and B, they look completely different shades of gray.
They do. Square A looks dark gray, square B looks much lighter, almost white. But if you actually measure the pixel values or isolate the squares, you find they are exactly the same shade of physical gray.
So why on earth do they look so different?
Because of the shadow. Your brain sees square B sitting inside a cast shadow, and your brain has a very, very strong prior belief. Shadows make surfaces look darker than they really are.
Okay, that's a learned role from experience.
A deeply ingrained one. So the brain reasons, unconsciously, if square B looks this gray while it's in a shadow, then its actual surface color, the paint on the checkerboard, must be much lighter than that. It corrects for the shadow.
So it presents us with its inferred reality, the corrected lighter color for B, rather than the raw data.
That's exactly it. It solves the ambiguity by applying its prior knowledge about shadows and gives you the interpretation, not the raw sensation. It shows how powerfully our expectations shape what we see.
That's incredible. If this predictive inferential process is so fundamental to how the brain works, it shouldn't just be about vision, right? Do we see similar things happening in other senses?
Absolutely. That's what makes the theory so compelling. We find illusions based on similar principles across different sensory modalities. It confirms this is a general brain strategy.
Like what? Any auditory example?
A great one is the Shepard tone. It's often called the auditory Penrose staircase, an impossible staircase for the ears.
I think I know this one. It sounds like a tone that is constantly rising in pitch, forever. Or constantly falling.
Exactly. It creates this compelling sensation of endless ascent or descent, but it never actually gets higher or lower overall.
How does it do that? It sounds impossible.
It's cleverly constructed using multiple sine waves separated by octaves. As the tones rise, the highest frequency components are subtly faded out, while new low frequency components are faded in at the bottom. Your brain focuses on the rising relationships between the tones it can hear clearly at any moment and doesn't notice the sneaky changes at the frequency extremes.
So it's tricking the brain's pitch perception system. And you mentioned Christopher Nolan uses this.
Famously. He used Shepard tones extensively in the score for Dunkirk to create that feeling of unbearable, unending tension. It works because it taps into this fundamental auditory illusion. It shows our hearing is also based on interpreting patterns, not just raw frequencies.
Okay, so vision and hearing. What about combining senses? Are there illusions that arise from, like, conflicts between senses?
Oh, definitely. And these are perhaps the most revealing about how the brain integrates information from different channels. The absolute classic here is the McGurk effect.
McGurk effect. What happens there?
It's a fascinating demonstration of vision influencing hearing. What happens is you show someone a video of a person's mouth making the lip movements for the syllable ga ga ga.
Okay, so ga ga.
But at the same time, you play an audio track of someone saying bump ba.
So my eyes see ga, but my ears hear ba. What do I perceive?
For a large number of people, the brain tries to resolve this conflict between visual and auditory input. It finds a compromise. What people often report hearing is a completely different syllable, like da da da.
Wow, it just fuses them into something new.
It fuses them, or rather the visual information, strongly influences the auditory perception. Your brain finds the best fit for the conflicting data, and da is often that best fit, phonetically sort of between ba and ga. It's powerful proof that speech perception isn't just auditory, it's inherently multisensory. Your brain expects lip movements and sounds to match up.
And you mentioned earlier that this effect can vary, like culturally.
Yes, that's another fascinating layer. Studies have shown that the strength of the McGurk effect can differ across language groups. For instance, some research suggests native speakers of Japanese or Mandarin might experience the effect less strongly or differently than English speakers.
Why would that be?
The exact reasons are still debated, but it might relate to how much different languages rely on visual cues, lip reading, and everyday communication, or differences in the phonetics of the languages themselves. But the fact that there is variation makes it a really valuable tool for researchers studying how sensory integration develops and how it might differ in clinical populations, like individuals with autism spectrum disorder or dyslexia.
That cultural variation point is really interesting, and it actually brings us perfectly to a huge historical debate in illusion research, specifically around that Müller-Lyer illusion. We talked about the lines with the fins.
Ah, yes, the nature versus nurture debate for illusions. For decades, this was a central question. Are we born wired to see these illusions, or do we learn them from our environment?
And the dominant theory for a long time was the learning side, right? The carpentered world hypothesis.
Exactly. proposed back in the 1960s by researchers like Seagal, Campbell, and Herskovitz. Their argument was pretty logical, based on that size constancy idea we discussed.
Remind us of the logic.
They argued that people living in carpentered environments, Western societies, basically full of buildings with straight lines, right angles, corners become highly accustomed to interpreting angular junctions as depth cues.
Like the corners of rooms or buildings?
Right. So the outward-pointing fins on the Müller-Lyer line look like a near corner, making the line seem closer and thus shorter. The inward-pointing fins look like a far corner, making the line seem farther and thus longer, thanks to that automatic size scaling.
And the hypothesis predicted that people who didn't grow up in such environments, maybe people living in cultures with predominantly round huts or more organic structures,
would be less susceptible to the illusion because they wouldn't have learned those specific depth associations as strongly. And early cross-cultural studies seem to support this. They found some non-Western groups showed a weaker Müller-Lyer effect.
So for a while, it looked like culture and learning were the primary drivers.
It did. It's a very compelling story. But then came the counter-evidence, and it's pretty overwhelming, leading to a significant reversal in scientific thinking. The evidence favoring an innate origin hypothesis started piling up.
Okay, what kind of evidence overturned the carpentered world idea?
Several lines of evidence, actually. First, cross-species evidence. It turns out that it's not just humans who see the Müller-Lyer illusion. Studies have shown that fish, birds, reptiles, even insects like bees, show responses consistent with perceiving the illusion.
Wait, fish, bees, they definitely don't live in carpentered worlds.
Not at all. So if they experience the illusion, it strongly suggests the underlying mechanism isn't based on learning about human architecture. It must be something more fundamental in visual processing, maybe related to how nervous systems generally process angles or contours.
Okay, that's pretty compelling. What else?
Second, haptic evidence. Haptic means related to touch. Researchers created raised line versions of the Müller-Lyer figures and had people explore them by touch while blindfolded.
So no visual input at all?
None. And guess what? People still experience the illusion. They judged the line with the inward fins as being longer, just by feeling it.
Wow, so it's not just a visual perspective trick, it works through touch too.
It does, which again disconnects it from the idea that it's learned specifically from visual perspective cues related to buildings. Touch doesn't work that way.
Okay, that's two strong points against the pure cultural learning idea. Was there anything else?
The third and perhaps most definitive piece of evidence came from clinical studies, specifically studies involving individuals who were born blind, due to cataracts, for example, and later had their sight surgically restored as children or adults.
People seeing the world for the very first time.
Exactly. A unique opportunity to test what's innate versus learned. And researchers found that these individuals experienced the Müller-Lyer illusion immediately upon gaining sight. They hadn't had years of living in a carpentered world to learn the cues. Their visual system seemed to be susceptible right out of the box.
So innate wiring, pretty much.
The consensus now leans heavily that way. While culture might modulate the strength of some illusions slightly, the basic susceptibility to illusions like Müller-Lyer seems to be rooted in fundamental, likely evolutionarily ancient, properties of neural processing, shared across species and sensory modalities. The carpentered world hypothesis, while logical, just didn't hold up against the breadth of evidence.
That's a fantastic example of the scientific process correcting itself. It really underscores that these perceptual mechanisms are deep-seated.
Absolutely. And understanding these deep mechanisms isn't just, an academic curiosity. These principles have real-world applications. Illusions are actually used quite intentionally in various fields.
Like in art, obviously. We mentioned M.C. Escher using paradox illusions. Op art is full of distorting illusions, too, creating effects of movement or vibration.
Definitely. Escher brilliantly merged mathematics and art. His waterfall literally uses a Penrose triangle structure. But beyond fine art, think about practical design. User interface and user experience UI/UX designers constantly have to account for potential visual illusions.
How so? Give us an example.
Okay, think about a simple triangular play button, like on a video player.
Yep.
If a designer centers that triangle perfectly geometrically within a square or circle button background, it won't look centered to the human eye.
Really? Why not?
Because there's something called the triangle bisection illusion. Our visual system tends to perceive the center of mass of a triangle as being slightly higher than its geometric center. So a geometrically centered triangle looks like it's floating up too high. It looks unbalanced.
So what do designers do?
They apply optical correction. They deliberately nudge the triangle down slightly from the geometric center until it looks visually balanced and centered to the viewer. They're compensating for the known illusion to achieve perceptual harmony. That happens all the time in typography and graphic design.
Huh, I never realized that. So they're fighting illusions with design tweaks. Any other cool applications?
Well, there's a really interesting safety application gaining traction, 3D crosswalks.
3D crosswalks, you mean they actually built them up?
No, they're just painted. But they're painted using principles of perspective and shadow to make them look like solid, raised blocks floating above the road surface when viewed from an approaching car.
Ah, so it's an illusion of a physical obstacle. Why do that?
To grab drivers' attention and make them slow down instinctively, the driver's brain sees what looks like a physical barrier you wouldn't want to drive over at speed, triggering a natural braking response. It's using perceptual psychology for road safety.
That's actually brilliant. Using an illusion to prevent accidents. Okay, so this all leads to a final, really important connection you hinted at earlier, the link between these perceptual illusions and, well, bigger errors in our thinking.
Exactly. This is where it gets really profound, I think. The very same kinds of mental processes, the reliance on assumptions, prior beliefs, mental shortcuts or heuristics that cause us to misperceive a line's length in the Müller-Lyer illusion, also operate at higher levels of cognition. They lead to what psychologists call cognitive biases.
So perceptual illusions are like misjudgments of the physical world outside.
Right. A systematic error in perceiving size or color or shape.
And cognitive biases are misjudgments of information, situations, people, systematic errors in thinking and decision-making.
Precisely. They are predictable patterns of deviation from rational judgment. Think of them as illusions of thought. The underlying mechanisms of the brain taking shortcuts, relying on patterns, being influenced by context are remarkably similar.
Can you give some examples of these cognitive biases that parallel perceptual illusions?
Sure. A really common one is confirmation bias. This is our tendency to actively seek out, interpret, favor, and remember information in a way that confirms our pre-existing beliefs or hypotheses. We ignore or downplay evidence that contradicts what we already think.
Which sounds a lot like the brain focusing on data that fits its prior beliefs in the Bayesian model.
It's very much analogous. And confirmation bias is everywhere, especially amplified today by things like social media filter bubbles, where algorithms feed us content that reinforces what we already like or believe.
Yeah, you end up in an echo chamber. What's another example?
How about the halo effect? This is where our overall impression of a person, often based on one prominent positive trait like physical attractiveness or charisma, influences how we judge their other unrelated characteristics.
So if someone is good-looking, we might automatically assume they're also more intelligent or more competent or kinder, even without evidence.
Exactly. That initial positive halo spills over and biases our subsequent judgments about completely different qualities. It's another mental shortcut, making a global judgment based on limited, easily accessible information, like judging the whole checkerboard based on the shadow.
So these biases, these illusions of thought, are just as systematic and predictable as the visual ones.
They are, and understanding them is crucial, because while misjudging the length of a line might not matter much, cognitive biases can have really serious consequences in areas like hiring decisions, medical diagnoses, financial investments, legal judgments, and even our social and political views.
That really brings us to the big takeaway then, doesn't it, for you, the listener? What's the core message from all this?
I think the most important thing to grasp is that the reality we experience is never a direct, unfiltered recording of the outside world. It is always an active construction, an interpretation, generated by the brain's predictive machinery based on ambiguous sensory input and its own internal models.
So we should be a bit more humble about how accurately we see things, both literally and figuratively.
Humble and critically aware. Recognizing that perception is an inference encourages us to question our own certainties, to consider alternative interpretations, and to be mindful of the shortcuts and biases, perceptual and cognitive, that shape our understanding.
It definitely makes you think twice about, I saw with my own eyes, or I know I'm right.
It should, and the science continues to push forward. What's next for illusion research? It's actually a really exciting time.
How so? What are the new frontiers?
Well, technologies like virtual reality, VR, and augmented reality, AR, are becoming incredibly powerful tools. They allow researchers to create fully immersive, precisely controllable sensory environments.
So you can manipulate sight, sound, even touch, all together in ways you couldn't before.
Exactly. You can study multi-sensory integration, like the McGurk effect, with much more complexity. You can create entirely novel, impossible environments to probe the limits of our perceptual models. It's opening up new ways to investigate consciousness itself.
And what about things like AI? Is that playing a role?
Definitely. Researchers are using artificial intelligence and machine learning models, particularly those based on predictive processing principles similar to the Bayesian brain idea, to test theories of perception.
How does that work? You see if the AI makes the same mistakes humans do.
Kind of, yes. You can train these models on sensory data and see if they develop susceptibility to the same illusions humans experience. It helps refine our understanding of the computational principles involved. Can we build an AI that sees the Canissa triangle or gets fooled by the Müller-Lyer illusion? If so, what does its internal processing tell us about our own?
Fascinating stuff. So the quest to understand why we see things that aren't there or see things differently than they are is actually helping us map the very nature of perception and thought.
That's the goal, to understand the rules of the brain's best guess system. Because ultimately, the world we perceive is always that best guess. And maybe the wisest approach is to treat that guess, both about the world out there and our own thoughts about it, with a healthy dose of curiosity and, yes, skepticism.
A perfect place to leave it. Really makes you reconsider everything you see. Thanks for tuning into this episode. If you enjoyed our content, don't forget to like, subscribe, share, and turn on the notification bell.